Okay, we've seen that this curve is a numerical integral of this curve. And again, if we knew the function here, we could get the exact curve here. The slope from here to here is going to be equal to the average force on the second interval. Okay, the slope of this graph for the second 1 centimeter interval from 2 centimeters to 3 centimeters is equal to the average force from 2 centimeters to 3 centimeters as indicated by this graph. And similarly for the other two intervals. In each interval, the slope of this graph is equal to the average force for the same interval on this graph. Okay, now we ask, what does that have to do with anything? And try to answer that question. Okay. What we want to do is we want to consider what happens if F is conservative force. If F is a conservative force, the question is, what does delta W from 1 centimeter to X mean? And what does the second graph then represent? Now, we said it represents an accumulated area under the first curve, but again, we're trying to get a handle on this delta W from 1 centimeter to the position X. Okay, we can express that as an integral, and you might already see what that integral ought to be. We'll get to that, but let's first interpret this calculation and the meaning of this quantity. Definition of potential energy, which incidentally we had some time ago, but nobody seemed to be able to give me that definition. Although we got some pretty close ideas on it. Okay, change in potential energy is defined to be the negative of the work done by the conservative force on the system that we're talking about. Okay, system for which we're trying to calculate the potential energy. Okay, change in potential energy is by definition equal to this quantity, the negative of the work done by the conservative force on the system. Another way to say that is it's equal and opposite to the work done by the conservative force and by the conservative force on the system. Okay. Now let's say that, let's just try to visualize this in terms of a familiar situation. Let's say F is the force exerted by the big magnet on the car. Then here's a graph of that force, and let's say here are 2 points. Okay, we might even call these points A and B. Maybe too small to see even with the better resolution here, but that's A and that's B. So the chalk just hit the floor. Work done between A and B is going to correspond to the area underneath this curve. The work done, the delta W from 1 centimeter to X, the work done from A to B. Okay. We're trying to get a handle on how this then relates to the change in potential energy. Well, if this force is exerted by the big magnet on the car, and if we move from A to B, then the change in potential energy is going to be negative because, well, let's stick to the definition. Could give you the intuitive reason for that, but we've already talked about that. Okay. If X is increasing, as it would be if we move from point A to point B, then we're getting positive work done by the conservative force. Change in potential energy is equal to the negative of the work done by the conservative force. So this implies a potential energy loss. That is, the change in potential energy is negative. Okay, again, this picture corresponds to positive work being done between this point and this point. You have a positive area under the graph, so you have positive work. which means that the work done by that conservative force in the system is positive, meaning that the change in potential energy is equal and opposite to that is negative. Okay, so if we move in this direction, loss of potential energy. If we move in this direction, we have a gain of potential energy. Because, of course, well, we'll get to the integral definition in a minute. So we see that the area beneath this curve between A and B is equal to the work done as we move from A to B. And that work is done by a conservative force, F being a conservative force. So that's equal to the negative of delta PE, the change in potential energy. And that area, of course, is equal to the integral from A to B of F dx. So the integral of the force with respect to position is equal to the area under the curve, as we know from the area definition, area connection. That's equal to the work from A to B. That's the definition of the work from A to B. And that's equal and opposite to the potential energy in the case where F is conservative. Now, the graph we have down here is what? This graph is the work done between 1 centimeter and position X. Okay, this is the complete graph. We approximated the graph, but the definition of this function here is the integral from 1 centimeter to X of F of X dx. And we see how that's related to the work done, to the area under the curve from 1 centimeter out to position X. So this is the work done from 1 centimeter to position X. This is the F of X function. And now the question is, how does this relate to the potential energy function? Well, the integral from 1 centimeter to X is equal and opposite to the change in potential energy between 1 centimeter and X. So this is equal to negative change of potential energy from 1 centimeter to X. And it looks like we need to move the camera over a little bit, okay? Because by the definition of potential energy, the change in potential energy is equal and opposite to this integral. Okay, this integral being the work done between 1 centimeter and X by the net force, by the conservative force. Let's go ahead and put the subscript conservative on here. Okay, equal and the work done by the conservative force is equal and opposite to the change in potential energy. Now, this is all within the context of the work energy theorem. The work done by non-conservative forces on the system is equal to the change in kinetic plus a change in potential energy. So let's think about some of the implications of that for a system under the influence of conservative force.